This is Bob Capetta from the University of Illinois at Chicago, and this is Taylor and Maclaurin series part 2. We're going to find the interval of convergence for our Taylor series for f of x equals natural log of x, centered at c equals 1. So this was the question that we looked at. Again, f of x equals log x at 1, and that is a general form of our Taylor series, and we determined what a0, a1, a2, a3. So in the last video, we did all that computation. A0 was 0, A1 was 1, A2 was negative a half, A3 was a third, A4 was negative 4. And from there we identified our form. So P of x is the sum as k goes from 1 to infinity of what? Well, you can see x minus 1 to the first over 1, x minus 1 to the second over 2, x minus 1 to the third over 3, x minus 1 to the fourth over 4. That's obvious. The sign flash requires a little bit of ingenuity. You can recognize that when k equals 1, this is a positive 1. When k equals 2, it's negative. So when k equals 1, it's positive. I'm going to need to take negative 1 to the k plus 1 to make that happen. K equals 1. 1 plus 1 is 2. Negative 1 to the second power is positive 1. So this is our form, and we want to go ahead and find the interval of convergence. So we're going to play with the ratio test. So how does that work? We're going to look at absolute a sub k plus 1. So with the absolute value, the sign flasher goes away. So we get x minus 1 to the k plus 1 over k plus 1. Hitting it with an absolute value, x minus 1 to the k plus 1 over k plus 1 will be absolute a sub k plus 1. Absolute a sub k, again, the sign flasher goes away. Absolute x minus 1 to the k over k, written this way, absolute x minus 1 to the k over k. If we're using the ratio test, we want to divide these two things. So absolute a sub k plus 1 divided by absolute a sub k, this divided by this. So change that division to multiplication. X minus 1 to the k plus 1 over k plus 1 times k over absolute x minus 1 to the k. So you'll notice x minus 1 to the k plus 1 divided by x minus 1 to the k just gives me an absolute x minus 1 times k over k plus 1. With the ratio test, we want the limit as k goes to infinity of this. And you can see as k goes to infinity, this thing is going to go to 1. So we're here, and the limit as k goes to infinity of that, recognize k is changing, so absolute x minus 1 can come out in front. Absolute x minus 1 times limit as k goes to infinity over k times k over k plus 1. But as k goes to infinity, this just goes to 1. And I get absolute x minus 1. With the ratio test, this will converge if that ratio is less than 1. Now, if it's equals 1, the test is inconclusive. If it's greater than 1, it diverges. But what I need is I need absolute value of x minus 1 to be less than 1. So negative 1 is less than x minus 1 is less than 1. X is between 0 and 2. And this is about where the last video ended. What I want to do now is I want to check the endpoints. I want to see if I plug 0 into this, does it converge? If I plug 2 into this, does it converge? So let's take a look. What is P of 0? Replacing x with 0, we get negative 1 to the k plus 1, 0 minus 1 to the k over k. Well, 0 minus 1 is just negative 1, and we have to ask ourselves, how does that work with the original piece? So I have negative 1 to the k plus 1 times negative 1 to the k. Well, we know if you have the same base, you add the exponents. K plus 1 plus k is 2k plus 1. Now, what is that? We have negative 1 to the 2k plus 1. Let's think about it. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. It's always negative 1 to an odd number. Negative 1 to an odd number will always simply be negative 1. And then we ask ourselves, does this converge or diverge? But negative 1 is a constant. That can come out in front. So we get negative 1 times the sum as k goes from 1 to infinity of 1 over k. But we recognize that this is the harmonic series. It diverges. So negative 1 times something going to infinity is certainly not going to converge. So we conclude on this piece that this diverges based on the fact that it's a harmonic series. But remember, our function f of x was natural log of x. And we're saying that our series diverges at 0. If it converged at 0, we would have a rule for natural log of 0, and we know 0 is not in the domain of the log function. So 0 is one of our endpoints. This Taylor series does not converge plugging in a value of x of 0. Now what was our other endpoint? That was 2. So if I'm looking at p of 2, how is that going to work? 2 minus 1 to the k over k, 2 minus 1 to the k. Well, 2 minus 1 is 1. 1 to the k is just 1. So you multiply anything by 1, you get the anything back. I have negative 1 to the k plus 1 over k. What's the status on this? This alternates. So it starts out negative 1 to the second. It starts out positive. Negative 1 to the third, negative. Positive, negative, positive, negative. This alternates. If I ignore the sign flasher, I have 1 over k. 1 over k's limit is 0, and it's decreasing. 1 over k plus 1 is less than 1 over k. So this whole thing converges by the alternating series test. So, of course, these are both 2's and not 0's. Let me fix those quick. So plugging in 2, we get an alternating series that converges. So this Taylor series converges when x is 2 based on the alternating series test. Well, if that's the case, what do we conclude? It converges at 2 and it diverges at 0. So our interval of convergence is that half-open interval, open at 0 and closed at 2. And that will conclude this lesson.